Hey everyone, today's journey rockets you up above Earth to the International Space Station. We begin with why it was a nightmare to dock a module on the ISS, as we relive every pulse of thrusters, every flicker of faulty sensors, and every diagnostic alarm that threatened to end the mission. Before you settle in, please like the video and subscribe if you haven't already. Your support keeps these high-stakes missions coming. We love seeing where in the world you're tuning in from, and what time it is in your corner of the globe. Now find a comfortable spot, imagine floating in microgravity, and brace yourself for the tension of precision docking. Prepare to feel the chill of the vacuum outside, hear the hiss of the airlock cycling, and witness the mechanical ballet that nearly ended in disaster. The International Space Station traces a luminous arc against the void 250 miles above Earth. From your position in the approaching module, this metallic behemoth appears deceptively still. But both your vehicle and the station hurtle through the vacuum at 17,500 miles per hour. The difference between catastrophic collision and perfect docking lies in the most minute adjustments of relative velocity. You feel the thruster pulses as gentle pushes against your back. Each burst lasts mere milliseconds, yet sends tremors through the module's aluminum skin. These vibrations transfer directly into your fingertips where they rest on the control panel. This is not the violent shaking of atmospheric flight, but something more subtle and precise. A language of mechanical feedback that experienced astronauts learn to interpret as intimately as their own heartbeats. The challenge begins with approach velocity. Too fast, and the energy of impact could damage both vehicles. Too slow, and orbital mechanics will drift you apart like leaves on a current. NASA procedure dictates closing at approximately 1/10 of a foot per second during final approach. This glacial pace means the last 10 feet of docking requires 100 seconds of perfect alignment and unwavering concentration. 100 seconds where a deviation of even 1 degree in attitude control, the module's orientation in space, compounds into misalignment measured in feet. Through the forward viewport, the station grows from a distant cruciform to a sprawling complex of modules, trusses, and solar arrays. The target docking port might be in shadow one moment, then blindingly illuminated the next as you cross the terminator between Earth's night and day. This transition happens 16 times every 24 hours, as the station completes each 90-minute orbit. The relative motion between vehicles creates an unsettling optical illusion. Sometimes the station appears to drift upward, sometimes laterally. Your brain, evolved for terrestrial movement, struggles to interpret this dance of orbital mechanics. The station isn't moving in these strange ways, rather your perception distorts as two massive objects attempt to synchronize their paths through space. Inside the approaching module, environmental systems hum steadily. The recycled air carries a faint metallic taste, tinged with the sterile scent of electronics and filtered oxygen. Temperature regulation keeps the cabin precisely controlled, yet you notice cold spots near the exterior walls where space's absolute zero lurks just inches away. Each thruster firing not only nudges the vehicle but consumes precious propellant. The mass of fuel available for docking maneuvers is strictly limited, calculated down to the gram. Run out during approach, and the mission faces abort. The fuel gauge becomes a constant companion in your peripheral vision, its slowly declining values adding pressure to every decision. Navigation relies on a complex system of relative sensors. Radar provides range data in tenths of a meter. Star trackers maintain absolute orientation by referencing the fixed points of distant suns. Laser rangefinders offer precision measurements to the docking port, yet no sensor is flawless. Each comes with error bars, noise, and potential failure modes that mission controllers track with statistical models and backup systems. The approach corridor narrows as distance decreases. At 100 meters, the acceptable cone of approach might span several meters wide. By 10 meters, this tolerance shrinks to inches. Any deviation requires correction, but overcorrection induces oscillation. The module could begin to swing like a pendulum, each thruster firing to dampen one movement while potentially starting another. Microgravity transforms the physics of fluid management. Propellant sloshes inside tanks despite baffle systems designed to minimize movement. This shifting mass subtly alters the module's center of gravity, requiring the flight computer to recalculate thruster firing solutions continuously. You can sometimes feel this as unexpected tugs or yaws that seem to come from nowhere. The mathematics of orbital rendezvous was pioneered during the Gemini program in the 1960s. These equations, refined over decades, govern every aspect of approach. When two objects orbit at different altitudes, they necessarily travel at different velocities. The higher object moves slower, the lower one faster. Matching these orbital parameters requires precise burns calculated to the millisecond. Velocity changes in space never end cleanly. Each thruster firing induces secondary effects, small rotational moments that must themselves be countered. Your module carries multiple thruster blocks, typically 16 individual engines arranged to provide control in all 6 degrees of freedom. Forward and backward, up and down, left and right, plus rotation along 3 axes, pitch, yaw and roll. Controlling all 6 simultaneously requires either a highly automated system or years of training for manual operation. The display before you updates with closing rate data, 0.1 feet per second, 0.09. The numbers fluctuate slightly with each sensor update. Behind these simple digits lies a cascade of calculations, with radar signals bouncing between vehicles, computer systems interpreting return times and algorithms filtering out noise from data. Visual indicators on the station's docking port appear first as dim outlines, then resolve into distinct patterns designed for both human and machine vision. Reflective material catches sunlight during dayside passes, while LED illumination provides visibility during orbital night. These markers establish the roll alignment crucial for proper docking mechanism engagement. The communication system crackles periodically with updates from mission control. Each transmission travels at light speed, yet still requires seconds to reach you in low Earth orbit. This delay reminds you of the physical distance separating you from Earth, despite the blue and white marble filling your side viewports. As distance drops below 50 meters, you enter the keep-out sphere, an imaginary boundary where approach procedures become even more stringent. Station systems monitor your trajectory with independent sensors, ready to trigger abort protocols if parameters exceed safety margins. The crew inside may have visually acquired your vehicle, watching through windows as you maneuver closer. The physics of orbital mechanics means you're not simply flying directly toward a stationary target. Both vehicles trace slightly different orbital paths, and your approach must account for these differences. The station itself isn't completely stable either. It flexes and bends with thermal expansion as sunlight heats its structure unevenly. Solar array adjustments can induce subtle vibrations. Crew movement inside shifts mass distributions by tiny but measurable amounts. Your breathing becomes shallower as concentration intensifies. The environmental control system registers this change, subtly adjusting oxygen flow. Condensation might form briefly on metal surfaces near your position, a small atmospheric response to your focused presence. Docking system activation begins at 20 meters. Power flows to electromagnetic components, mechanical latches prepare for engagement, and pressure sensors come online to verify future seal integrity. You feel a slight change in the electrical hum surrounding you as systems draw additional power. The closing rate drops further, 0.07 feet per second. Progress seems agonizingly slow, yet this pace is precisely calculated. Any faster would build momentum that might be difficult to arrest if an abort becomes necessary. At 10 meters, the docking system's soft capture sensors activate. These will provide the initial connection before the hard capture system firmly secures the vehicles together. Alignment guides extend visually, resembling an elaborate target system. Your task is to center the approaching mechanism precisely within these guides. The relative velocity has been reduced to mere centimeters per second. At this range, even breathing seems too forceful an action. Your hands hover near the manual override controls, ready to intervene if automated systems falter. Visual perception becomes critical now. Shadows can deceive, creating illusions of distance and alignment. The human eye, evolved for terrestrial hunting and gathering, struggles with the harsh contrasts of space. What appears as perfect alignment from one angle might reveal misalignment from another. This is why multiple camera views supplement direct visual observation, providing perspective from various points around the docking mechanism. The station's mass dwarfs your module by factors of hundreds. This disparity means that contact, even gentle contact, primarily affects your vehicle's momentum rather than the station's, like a rowboat bumping against an aircraft carrier. The smaller object absorbs most of the interaction energy. At 5 meters, you can detect the space station's presence not just visually but physically. Minute gravitational effects become theoretically measurable, though overwhelmed by more immediate forces. More noticeable is the reflection of sunlight off the station's surfaces, creating complex patterns of illumination that dance across your controls. The final moments of approach reduce to a study in patience. The distance closes at what seems like geological timescales. Individual seconds stretch as your awareness heightens. The environmental systems which had faded to background noise during intense concentration suddenly seem louder again. The recycled air carries traces of electronics, insulation, and the unique olfactory signature of machinery operating in vacuum conditions. 1 meter separation. The docking port fills your field of view. Alignment indicators show green status across all parameters. The approach velocity holds steady at its minimum sustainable rate. Any slower and positional uncertainty would exceed forward momentum, risking drift off centerline. Then contact, a sensation more felt than heard. The gentlest bump propagates through the structure. Soft capture sensors register successful initial connection. Small hooks engage temporarily, establishing a tenuous link between vehicles. This preliminary connection remains fragile, easily broken if alignment proves inadequate for the subsequent hard capture process. But this initial touch between spacecraft represents merely the beginning of docking's challenges, as capture sensors transmit their confirmation signals. Another more insidious problem lurks within the complex interplay of light and shadow surrounding the station. The human vision system, even augmented by cameras and sensors, must now contend with extreme contrasts that can obscure crucial visual references. The next phase brings new complications as perceptual systems struggle against the harshest visual environment humans have ever operated within. The initial contact between your module and the International Space Station creates a momentary equilibrium, but this balance exists on a knife edge. Your vision, your primary sensory connection to this extraordinary environment, now becomes both your greatest asset and most dangerous liability. In the vacuum of space, light behaves in ways that confound human perception, creating illusions that can transform routine operations into nightmarish challenges. The first obstacle rises literally before your eyes. Sunlight in space arrives unfiltered by atmosphere, carrying its full spectrum of energy, including ultraviolet and infrared wavelengths that Earth's blanket of air normally attenuates. This raw solar radiation strikes the station's metallic surfaces and creates a glare so intense it can temporarily blind both human eyes and camera sensors. The effect resembles staring into automobile headlights on a midnight road, but multiplied hundredfold. Your pupils contract painfully as you instinctively turn away. The viewport automatically darkens using electrochromic technology, similar to transition sunglasses but responding in milliseconds rather than minutes. Even with this protection, the contrast remains extreme. The sunlit portions of the station blaze with unbearable brightness while adjacent areas in shadow disappear into absolute darkness. Your retinas, evolved for Earth's gentle lighting conditions, struggle to adapt to this binary visual environment. Camera systems fare no better. Their digital sensors, despite advanced high dynamic range capabilities, cannot simultaneously capture detail in both the brightest highlights and darkest shadows. Engineers designed automated exposure control algorithms to rapidly adjust, but these systems can lag during sudden transitions from darkness to light. During these momentary adjustment periods, crucial alignment markers might be invisible, hidden in overexposed glare or underexposed shadow. The docking port itself might vanish into darkness as the station's complex geometry casts shifting shadows. The International Docking Adapter, a precisely machined structure of aluminum and steel, alternates between invisible darkness and blinding reflection depending on orbital position. Finding the alignment guides becomes a test of patience and perception, waiting for that brief moment when illumination provides clarity before shadows return. This visual challenge intensifies during what astronauts call the Terminator crossing, the boundary between Earth's day and night sides. As the station passes through this transition 16 times daily, the lighting conditions change dramatically within seconds. Materials designed to be visible in darkness suddenly reflect blinding sunlight. Shadows shift rapidly across surfaces, creating illusory movement. Your brain, attempting to process these changes, can produce the disconcerting sensation that the docking port itself is moving when in reality only the lighting has changed. Inside your module, electronic displays provide crucial telemetry, but these screens themselves create new visual complications. Their illumination, calibrated for consistent readability, now competes with the extreme external lighting conditions. Your eyes must constantly readjust between the moderate brightness of instruments and the harsh contrasts outside. This visual toggling induces eye fatigue and increases the potential for misreading critical data. The reflective properties of materials in space add another layer of perceptual confusion. Multi-layer insulation, the gold or silver blankets covering much of the station's exterior, creates mirror-like surfaces that reflect both sunlight and your own approaching vehicle. These reflections can generate ghost images, duplicate visual references that trick the brain into seeing alignment markers or features where none exist. Distinguishing between an actual structural element and its reflection requires constant mental processing. Temperature differentials across the station's surface create subtle distortions through thermal expansion. Metal components on the sun-facing side might expand by millimeters compared to identical parts in shadow. While seemingly insignificant, these tiny variations can affect docking alignment when precision is measured in fractions of an inch. The visual effect resembles heat waves rising from hot pavement, a barely perceptible shimmering that distorts straight lines and precise edges. Distance perception, already challenging in the vacuum environment where familiar atmospheric cues are absent, becomes further complicated by these thermal distortions. The human visual system uses slight haziness at distance, a phenomenon called atmospheric perspective, to judge how far away objects are located. In space, objects hundreds of meters distant appear with the same clarity as those within arm's reach, removing this evolutionary perceptual tool. Radar and LiDAR sensors provide numerical distance measurements, but reconciling these abstract figures with visual perception creates cognitive dissonance. Your brain receives conflicting information, with eyes suggesting one distance while instruments indicate another. This sensory disagreement can manifest as space adaptation syndrome, a form of motion sickness where the inner ear and visual systems provide contradictory information about movement and position. During orbital night, artificial illumination creates its own perceptual challenges. LED arrays and spotlight systems attempt to illuminate the docking port, but their directional nature creates new shadows that can obscure critical features. These lights, necessarily power-limited, provide illumination far dimmer than sunlight, requiring both human vision and cameras to operate at the limits of their low-light capabilities. The approach cameras employ digital enhancement to brighten these nighttime images, but this processing introduces electronic noise, a visual static that resembles snow on an analog television. This noise can obscure fine details precisely when they matter most. Worse, the image processing algorithms sometimes create artifacts, digital anomalies that appear as structural features but exist only in the enhanced image. Throughout this visual chaos, your eyes constantly search for the alignment markers crucial for successful docking. These markers, typically contrasting patterns designed for visibility, now flicker between appearance and disappearance as lighting conditions change. The soft capture system requires alignment within 2 inches of center and 1 degree of rotational offset, tolerances that demand visual precision despite these perceptual obstacles. The station itself isn't a static target. Its structure experiences subtle flexing as thermal expansion and contraction forces work across its 100+ meter span. This movement can displace the docking port location by small but significant amounts. Visually tracking these shifts requires distinguishing between actual structural movement and the illusory motion created by changing light conditions. Your helmet visor adds yet another visual complication. Designed to protect against radiation and micrometeoroids, its polycarbonate construction introduces subtle distortions, particularly at the edges of your visual field. Keeping the docking port centered in your vision becomes essential not just for operational reasons but to minimize these optical aberrations. Inside the space station, astronauts might be watching your approach through windows or on monitors. Their perspective differs from yours, potentially allowing them to see alignment issues invisible from your vantage point. Their observations reach you through communication channels, adding another layer of information that must be integrated with your direct perception and instrument readings. The final approach phase activates proximity operations sensors, additional systems designed to provide ultra-precise measurements as distances decrease to mere feet. These sensors project structured light patterns onto the docking mechanism, patterns invisible to human eyes but detectable by specialized cameras. The computer interprets these patterns to calculate exact positioning data, adding yet another stream of information to process. Your perception narrows with concentration, inducing a phenomenon similar to tunnel vision. Peripheral awareness diminishes as focus intensifies on the docking port alignment. This attentional narrowing, while necessary for precision tasks, creates vulnerability to unexpected events outside the immediate field of focus. The physical sensation of the initial soft capture remains subtle, a gentle connection that might be missed amid the sensory complexity of the moment. Confirmation comes primarily through instrument readings rather than tactile feedback. Green status indicators illuminate, confirming that capture latches have engaged successfully despite the perceptual chaos surrounding the operation. Yet even with successful soft capture, the docking process has only begun. The misalignments and corrections during approach have induced energy into the system, creating gentle oscillations between vehicles. These movements, though minimal, must dampen completely before the hard capture system can engage. Through the viewport, you might notice the station appearing to move slightly, a rocking motion measured in millimeters but crucial to monitor. The thermal environment continues its assault on perception. Direct sunlight heats exposed surfaces to hundreds of degrees Fahrenheit, while adjacent shadows plunge to nearly absolute zero. This extreme temperature gradient creates not just visual distortions but physical ones as materials expand and contract. The docking mechanism itself, designed with thermal considerations in mind, nevertheless responds to these conditions with microscopic dimensional changes. Inside your module, environmental systems work continuously to maintain habitable conditions. Their operation creates another sensory layer, a background symphony of fans, pumps, and air circulation that forms the technological heartbeat of your spacecraft. This ambient sound helps mask the unsettling silence outside, where vacuum prevents direct sound transmission despite the complex operations underway. The module's internal atmosphere carries its own sensory signature. Recycled air passes repeatedly through scrubbers and filters, taking on subtle characteristics impossible to replicate on Earth. The slightly elevated carbon dioxide levels, still within safe parameters but higher than terrestrial norms, might induce a barely perceptible increase in respiration rate. The controlled humidity creates a distinctive feel against exposed skin, neither completely dry nor noticeably damp. Your communication with mission control continues throughout this process, their voices reaching across thousands of miles to provide guidance and confirmation. Their perspective, informed by telemetry streams but divorced from direct perception, offers both valuable oversight and occasional disconnection from the immediate reality of your situation. The slight transmission delay serves as constant reminder of the physical distance separating you from Earth support. As the soft capture system maintains its tenuous hold, the visual challenges evolve rather than disappear. The slight relative movement between vehicles means lighting conditions across the docking interface continue to change. Shadows shift minutely, reflections appear and vanish, and alignment markers move in and out of optimal visibility. Maintaining awareness of these conditions requires constant visual adaptation. The next phase will activate the hard capture system, drawing the vehicles together with motorized bolts to create an airtight seal. This process introduces new forces into the delicate equilibrium currently established between spacecraft. But before this can begin, another potential hazard emerges from the complex interaction between computer systems and human control inputs. The thrusters, which have brought you successfully to initial capture, now pose a different kind of threat. Thruster control systems, designed for exceptional precision, must now transition to an even more delicate operational mode. With vehicles in direct physical contact, any thruster firing carries the risk of exceeding structural load limits at the connection point. What happens when these precisely calibrated systems encounter the unpredictable variables of actual operation in space? The answer lies in understanding how easily a minor correction can cascade into a dangerous overcorrection. The gentle contact of soft capture has established a tenuous connection between your module and the International Space Station, a mechanical handshake across the void. But this union remains fragile, vulnerable to disruption from the very systems designed to facilitate it. The reaction control system thrusters, your primary means of maneuvering in space, now become potential sources of catastrophe through a phenomenon engineers call thruster overcorrection. You feel it first as a subtle vibration transmitted through the structure. One of the automatic control thrusters has fired, a brief millisecond pulse intended to dampen oscillation between the vehicles. But instead of stabilizing the connection, this impulse sends a shudder through the joined spacecraft. The sensation travels from the docking mechanism through the module's aluminum frame and into your body. A metallic twang followed by an unsettling lateral movement. The physics of this situation involves complex interactions between two massive objects temporarily linked by relatively delicate connection points. The International Space Station, with its 425-ton mass, dwarfs your approaching module. This mass disparity means that forces applied at the connection point create a fulcrum effect, with movements amplified along the length of both structures. Your module responds more dramatically to these forces due to its smaller mass, while the station experiences subtler but still significant effects. Thruster systems operate through binary commands, either firing or not firing. There is no throttle or variable output. Control comes through precisely timing the duration of these firings, typically in pulses as brief as 10 milliseconds. At the approach velocities required for docking, even these minimal pulses can impart more momentum than desired when systems are not perfectly calibrated for the joined configuration. The flight control software now faces a fundamental challenge. Its algorithms were designed for free space maneuvering of an independent vehicle, not for the complex dynamics of two massive objects temporarily linked. The software attempts to compensate for the initial overcorrection by firing opposing thrusters, but this response itself may be excessive. A dangerous feedback loop begins to develop. You experience this cascading correction problem as increasingly severe oscillations. What began as a gentle vibration grows into a disconcerting rhythmic movement. Through the viewport, you observe the station appearing to sway, though in reality both vehicles are moving in relation to each other. Instrument panels flash warning indicators, as sensors detect unexpected rates of angular change. The physical sensation intensifies. Each thruster firing now produces enough force to gently press you against your restraints. The motion resembles an elaborately complex pattern, not simply back and forth but including elements of rotation along multiple axes. This 6-degree of freedom movement cannot be easily predicted or counteracted with intuitive control inputs. Inside the module, unsecured items begin to drift in strange patterns, responding to these subtle accelerations. A water droplet that had been floating peacefully now zigzags through the cabin, tracing the invisible forces at work. Equipment stowed in retention nets strains against its constraints. The sounds change too, as the structure experiences stresses it was not primarily designed to withstand. The root causes of thruster overcorrection include several interlocking factors. Propellant sloshing within tanks creates unpredictable mass distribution changes that alter the module's center of gravity. Each thruster firing shifts this fluid slightly, meaning the next firing occurs under slightly different conditions than calculated. Temperature variations across the propulsion system affect valve response times by microseconds, enough to alter thrust duration meaningfully at these precision scales. Mission Control registers these anomalies through telemetry feeds, but their ability to assist remains limited by both communication delay and the split-second timing required for correction. Their voices in your headset maintain professional calm while conveying increasing urgency. The guidance computer presents multiple alerts now, some contradicting others as different systems interpret the complex motion differently. The station's massive solar arrays present particular vulnerability during these oscillations. These panels, spanning 240 feet tip to tip, can flex only within certain limits before risking structural damage. Their movement, visible through your viewport during particularly severe oscillations, adds another layer of urgency to resolving the situation. Similar concerns apply to other extended structures including radiators, antennas and robotic manipulation systems. Your training for this contingency emphasized one critical response: inhibiting automatic thruster firings. Your hand moves toward the control panel, fingers finding the reaction control system override switch through muscle memory. Flipping this switch transfers authority from the computer's increasingly problematic correction attempts to manual control or a more basic stabilization mode. The moment your fingers activate this switch, the pattern of thruster firings changes noticeably. The rapid, seemingly random pulses cease, replaced by calculated silence. The oscillations continue from existing momentum, but without additional energy being added to the system. Gradually, the natural damping effects of the connected structures begin to assert themselves. This passive damping occurs through energy dissipation within materials. Each flexion of metal components converts small amounts of kinetic energy to heat through internal friction. The rubber and composite elements within the docking system absorb energy through compression and expansion. Without additional thruster firings adding new energy, these damping effects slowly reduce the oscillation amplitude. During this damping period, your senses heighten to monitor the decreasing motion. The vibrations through your fingers on the control panel grow subtler. Visual references show the alignment gradually stabilizing. The sounds of stress within the structure diminish from concerning creaks to occasional pings as materials return toward their nominal positions. The telemetry displays confirm what your sensors detect. Angular rotation rates decrease across all three axes, approaching zero. Position indicators show the docking mechanisms returning to proper alignment. Temperature sensors along structural components register the slight warming from energy dissipation, fractions of a degree that nevertheless confirm the physics at work. Mission Control acknowledges the improving situation but recommends maintaining manual control mode temporarily. Their caution reflects hard-earned wisdom from previous docking operations where premature reactivation of automatic systems reintroduced instability. The station crew, monitoring from their perspective, reports their own observations of decreasing motion. With oscillations sufficiently damped, attention returns to completing the docking sequence. The hard capture system must now activate to create a sturdy airtight connection between vehicles. This system uses motorized hooks to pull the docking mechanisms firmly together, compressing seals and establishing structural continuity. Initiating this system while residual motion persists could damage delicate components. Your module's environmental systems have responded to the stress of the situation. Temperature control adjusts to compensate for the additional heat generated by both equipment and human occupants during the incident. Humidity management processes the moisture from accelerated respiration. Carbon dioxide scrubbers work slightly harder to manage elevated output. These automatic adjustments maintain life support parameters within nominal ranges despite the crisis. The physical toll on your body becomes apparent only as the emergency subsides. Muscles that tensed unconsciously now release, sometimes trembling slightly from sustained contraction. Your breathing pattern, which shallowed during intense concentration, deepens again. Heart rate, elevated by stress response, begins gradual normalization. These physiological signs mirror the spacecraft's own return to stability. The view through the viewport has stabilized now. The station's massive structure no longer appears to sway relative to your position. The docking mechanism alignment guides show proper positioning once more. External cameras confirm that no visible damage occurred during the oscillation event, though thorough inspection will follow completion of docking. With stability re-established, you must now decide whether to proceed with hard capture or initiate an abort sequence. This decision balances multiple considerations including propellant reserves, mechanical system status, mission timeline impacts, and risk assessment. The conservative approach would recommend undocking and attempting a fresh approach. The practical reality of limited resources sometimes necessitates proceeding despite less than ideal circumstances. Mission Control weighs in with their assessment, based on telemetry analysis. Their recommendation carries significant weight, but not absolute authority. As the on-site operator with direct sensory information, your judgment remains crucial. This moment exemplifies the fundamental partnership between ground-based expertise and on-orbit execution that defines spaceflight operations. The decision reaches you not as sudden clarity, but as gradual consensus emerging from multiple inputs. Instrument readings show systems return to nominal parameters. Visual confirmation through viewports validates alignment. Communication with station crew confirms their readiness. Your own physical senses detect no lingering anomalies. Collectively, these sources build confidence sufficient to proceed. Reactivating the automated docking sequence requires deliberate steps to prevent recurrence of the overcorrection problem. Thruster control parameters receive updated constraints based on the observed behavior. Automatic firing thresholds adjust to require larger deviations before activation. The software essentially becomes more conservative in its response profile while maintaining necessary intervention capability for genuine emergencies. The hard capture sequence begins with activation of motorized hooks. You feel the engagement as a series of gentle tugs transmitted through the structure. Each hook individually tensions and locks, creating an increasingly rigid connection between vehicles. What started as the tenuous handshake of soft capture transforms into the firm embrace of structural integration. The process resembles tightening bolts in a circular pattern, gradually and evenly establishing connection. Pressure sensors confirm proper compression of the docking seals, the rubber-like materials that will maintain atmosphere when the hatch eventually opens. The final hook engagements produce audible clicks as mechanisms reach their fully seated positions. Status indicators transition from amber processing notifications to green completion confirmations. The docking procedure, despite its harrowing complications, approaches successful conclusion. Yet the thruster overcorrection incident leaves lingering effects beyond the immediate crisis. Each firing consumed precious propellant, potentially affecting future operations if reserves fall below critical thresholds. The structural stresses, while within design tolerances, nevertheless accumulated fatigue in critical components that may require later inspection or maintenance. Most significantly, the event highlighted vulnerabilities in control systems that engineers will need to address for future missions. Your module has now physically joined the International Space Station, becoming part of the largest human-made structure ever to orbit Earth. The hard capture system provides not just physical connection, but also electrical and data interfaces that allow your systems to integrate with station resources. Power connections establish shared electrical supply. Data buses link computer systems. Eventually, atmosphere will flow between the environments once pressure equalization completes. But this success, hard-won through crisis management and technical expertise, opens the door to yet another challenge in the complex ballet of orbital operations. Even with physical connection established, the transfer of information between your module and the station must overcome its own set of obstacles. The next critical phase faces an invisible but equally dangerous adversary in the form of communication delays and command latency, where messages between systems travel not instantaneously, but through the tyranny of light speed limitations and processing bottlenecks. With physical connection established between your module and the International Space Station, information now becomes the critical resource. Computers must exchange thousands of parameters. Systems must synchronize across multiple platforms. Controllers must coordinate operations between ground stations and both spacecraft. Yet in this realm of electronic communication, time itself becomes your adversary in the form of delays and latency that transform simple data exchange into agonizing suspense. The first hint of this invisible challenge appears on your communications panel. The signal strength indicator shows full connectivity, yet the acknowledgement from station systems takes noticeably longer than expected to appear on your display. This delay, though measured in fractions of seconds, creates a distinct cognitive dissonance. Your action occurred, the system appears functional, yet confirmation lags behind expected response time. Command latency in space operations stems from multiple sources working in series and parallel. The physical distance between Earth and your orbital position imposes a minimum delay based on light speed. Radio signals traveling from ground stations must cover approximately 250 miles, requiring about 1.5 milliseconds each way under ideal conditions. This represents the absolute minimum physics will allow, the speed limit of information itself. But actual communication paths rarely achieve this theoretical minimum. Signals route through multiple ground stations depending on orbital position. Processing occurs at each node in the network. Authentication systems verify command integrity. Radiation effects in space occasionally corrupt data packets, requiring retransmission. These compounding factors extend response times from milliseconds to seconds. You experience this delay most acutely during critical system transitions. The docking mechanism requires precise sequencing between your module and station hardware. Initiating hatch depressurization from your control panel should trigger corresponding valve operations on the station side. But after sending the command, nothing happens immediately. The system shows processing status as signals traverse the complex path between vehicles and their respective control systems. Inside your module, environmental systems continue maintaining life-supporting conditions, their steady operation a counterpoint to the communication uncertainty. Air circulation fans create gentle background noise, occasionally changing pitch as automatic adjustments respond to temperature or pressure variations. The recycled atmosphere carries its unique blend of filtered oxygen, equipment emissions and human presence, a scent unmistakable to anyone who has spent time in spacecraft. The sensory experience of command latency manifests as a peculiar suspension of time. Your action has committed, yet remains unrealized in effect. This gap between initiation and confirmation creates space for doubt. Did the command transmit correctly? Were parameters within acceptable ranges? Has some unforeseen circumstance interrupted normal operations? These questions flood consciousness during particularly extended delays. Mission Control experiences these same delays from their perspective, creating a conversational rhythm unique to space operations. Their questions reach you, then your responses take equally long to return. This communication pattern leads to specific protocols designed to minimize misunderstanding. Information gets packaged efficiently, acknowledgements become ritualized, and patience becomes procedural rather than personal. The physical sensation of waiting during these delays affects your body subtly but noticeably. Breathing unconsciously slows or temporarily pauses while anticipating confirmation. Muscles incrementally tense, particularly in the shoulders and hands. Blink rate decreases as attention fixes on display screens. These autonomic responses reflect the brain's effort to prepare for potential contingencies during information gaps. The most challenging communication delays occur during automation sequences that cannot be easily interrupted once initiated. The docking mechanism transitions from soft capture to hard capture through multiple electrical and mechanical steps. Starting this sequence commits both vehicles to completion barring emergency abort. The commands to begin this process disappear into the communication system, leaving you momentarily disconnected from the outcome until confirmation returns. This waiting period has distinct psychological effects. Time perception distorts, with seconds seeming to stretch substantially longer than their actual duration. Attention hyperfocuses on any potential feedback, sometimes creating illusions of response where none yet exists. The brain's pattern recognition systems work overtime, occasionally interpreting normal system noise as meaningful signals. These effects compound the technical challenges with human perceptual complications. When responses finally arrive, they often come in bursts rather than steady streams. Multiple status updates held in processing queues suddenly appear simultaneously on displays. This information flood requires rapid sorting and prioritization, distinguishing critical parameters from routine acknowledgements. Your training emphasized developing this skill specifically for managing communication latency situations. The station's onboard systems face similar challenges communicating with your module. Their commands must traverse interface adapters, protocol converters, and security verification procedures. Different spacecraft often use different data formats and communication standards, requiring translation layers that introduce additional processing time. These compatibility solutions, while necessary, add their own delays to every interaction. Temperature variations contribute yet another variable to communication reliability. As spacecraft transition between sunlight and shadow, electronics experience thermal cycling that affects performance. Communication equipment, designed to operate across extreme temperature ranges, nevertheless performs optimally within narrower bands. During particularly cold or hot conditions, transmission power and receiver sensitivity may require automatic adjustment, adding processing time to communications. The physical infrastructure supporting communication contains potential bottlenecks that manifest during high-demand periods. Data buses within spacecraft have finite bandwidth. Processor cycles must be allocated between competing systems. Memory buffers can temporarily fill during data-intensive operations. These resource limitations become most apparent during docking operations when multiple critical systems simultaneously require communication pathways. Your display finally confirms successful initiation of the hard capture sequence. The motorized hooks have begun their coordinated movement, gradually pulling the docking interfaces together. But even this confirmation arrives with qualification, showing data freshness indicators that reveal the information is already seconds old upon receipt. The actual mechanical operation is always slightly ahead of your awareness of it, a constant reminder of information latency. Radiation effects in the space environment introduce yet another communication challenge. High-energy particles occasionally impact electronic components, causing momentary disruptions called single-event upsets. These events can corrupt data packets, requiring error detection and correction systems to identify and repair or request retransmission. During periods of heightened solar activity, these interruptions occur more frequently, extending average communication delays. The psychological impact of these delays compounds with mission duration. Early in operations, the gaps between command and confirmation seem manageable, even expected. As hours extend to days, however, the cumulative stress of perpetual uncertainty grows more taxing. Studies of astronaut performance show measurable effects on decision-making processes when operating under sustained communication latency conditions. The most dangerous situations arise when emergency responses require immediate coordination between systems. If a micrometeoroid were to impact near the docking mechanism, damage assessment and response would need to occur across multiple systems with minimal delay. The communication architecture, normally acceptable for routine operations, suddenly becomes a liability when milliseconds matter. Contingency procedures specifically address these scenarios with local automated responses designed to operate independently when necessary. You observe another manifestation of command latency and system synchronization challenges. The space station operates on its own internal timing reference, while your module maintains independent time standards. Though both ultimately reference atomic clock signals from Earth, subtle differences accumulate. Critical operations requiring precise timing must account for these discrepancies, adding another layer of complexity to command execution. The environmental control and life support systems demonstrate particular sensitivity to communication delays. Atmosphere management between newly connected spacecraft requires careful coordination of pressure equalization. Commands to open valves must execute in specific sequences with confirmation of each step before proceeding. Delays in these confirmations extend the equalization process from minutes to potentially hours, consuming crew time and mission resources. Your body responds to these extended operations with its own signals. Eyes fatigue from sustained focus on displays. Minor dehydration sets in, as attention to personal needs diminishes during critical phases. The central nervous system, continuously maintained in heightened alertness by operational uncertainty, begins showing efficiency decreases measurable in reaction time tests. These human factors interface directly with the technical challenges of command latency. The radio frequency environment surrounding the space station adds yet another variable to communication reliability. Multiple systems transmit simultaneously across various frequencies, occasionally creating interference despite careful frequency planning. External sources including Earth-based transmitters, solar radiation, and even distant astronomical objects contribute to the background noise floor against which your signals must be distinguished. Signal processing algorithms continuously adapt to these changing conditions, sometimes requiring additional time to extract valid commands from noisy channels. As hard capture completes successfully despite these communication challenges, pressure equalization between vehicles becomes the next critical operation. This process requires opening valves in careful sequence to gradually match atmosphere between your module and the station. Each valve command disappears into the communication system, followed by that now familiar delay before confirmation. The physical sensation of pressure changes, felt in your ears as subtle pops or in your sinuses as slight pressure, often arrives before electronic confirmation appears on displays. The hatch opening procedure exemplifies the operational impacts of communication latency. What should be a straightforward sequence expands to consume substantial time as each step requires verification before proceeding. Release locking mechanisms. Confirm, retract sealing interfaces. Confirm, initiate handle rotation. Confirm, each confirmation experiences communication delay, transforming a 10-minute procedure into 30 minutes or more of intermittent activity and waiting. Your training for these situations emphasized developing a specific psychological approach. Rather than experiencing delays as interruptions to workflow, you learn to incorporate them as integral components of the procedure itself. This mental framing helps maintain operational rhythm despite irregular feedback intervals. The technique resembles how musicians use rests as intentional elements of composition rather than mere absences of sound. The successful management of these communication challenges represents a triumph of both technology and human adaptation. Systems designed with latency tolerance, procedures structured to accommodate confirmation delays, and personnel trained to operate effectively despite information gaps collectively transform a potentially impossible situation into a manageable if demanding operational environment. But as the docking operation progresses toward completion, another physical challenge emerges from the complex mechanical interfaces now joining your spacecraft to the station. The soft capture system has performed its initial function and hard capture has secured the primary structural connection. Yet within the intricate machinery of the docking ring, subtle misalignments and temperature-induced stresses create the conditions for one of the most dreaded scenarios in spacecraft operations: mechanical jams in the precisely engineered capture system that must function flawlessly to maintain vehicle integrity. The transition from hard capture completion to operational docking should proceed with mechanical precision. Yet as pressure equalization initiates, an unexpected vibration travels through the structure. The sensation reaches your fingertips first, a discordant tremor distinct from normal operation. Then comes the sound, a subtle grinding that stops abruptly. Warning indicators illuminate on your control panel. The soft capture ring, which should now be retracting to allow full structural connection, has encountered a mechanical jam. This development transforms the atmosphere inside your module. The environmental systems continue their steady work, circulating air and managing temperature, but human tension alters your perception of the space. The recycled air suddenly seems thinner. The background hum of equipment takes on ominous undertones. The confined volume of the cabin, previously functional and familiar, now feels constrictive as uncertainty grows. The soft capture system represents one of the most complex mechanical assemblies in spacecraft design. Unlike most space systems that minimize moving parts to reduce failure points, docking mechanisms require intricate articulation. The system contains spring-loaded guides, motorized latches, rotating rings and multiple sensor arrays, all designed to operate in the extreme temperature variations of space, while maintaining precise alignment tolerances measured in millimeters. Your display shows the specific nature of the malfunction. The capture ring, which should rotate to align structural hooks for maximum force distribution, has stopped at 37 degrees into its 90-degree travel. Torque sensors show increasing resistance beyond expected parameters. Position indicators confirm the mechanism is neither advancing nor returning to its starting configuration. The system is physically stuck between states. The primary causes of mechanical jams include several possibilities, each requiring different resolution approaches. Thermal binding occurs when adjacent components expand or contract at different rates due to temperature gradients. Foreign object debris, though meticulously prevented during manufacture and assembly, occasionally manifests during operations. Lubricant issues arise in the vacuum environment, where special formulations must function without evaporation or viscosity changes across extreme temperature ranges. Mechanical tolerance stack-up results when minor variances within acceptable ranges for individual components combine to exceed system-level tolerances. The physical experience of this malfunction contrasts sharply with previous challenges. Unlike thruster overcorrection that produced dramatic motion, or communication latency that created psychological suspense, this mechanical jam manifests as absolute stillness when movement should be occurring. The expected progressive thunks and clicks of mechanism engagement are replaced by uncomfortable silence. This absence of expected feedback creates its own form of tension. Mission Control responds immediately to the telemetred warning signals. Their voices maintain professional composure, but subtle changes in speech patterns convey heightened concern. Their requests for specific sensor readings and system states reflect the troubleshooting protocols developed through decades of spacecraft operations. Each question builds their mental model of the situation, while simultaneously revealing potential recovery options. Your training for mechanical contingencies now guides your actions. The first step involves attempting normal operation again, essentially re-attempting the command sequence to determine if the jam was momentary or persistent. Your fingers move across the control panel, selecting retraction command options. The system accepts the input. Operation indicators show command processing, but physical feedback confirms the mechanism remains obstructed. The jam persists despite basic recovery attempts. The station crew, monitoring from their side of the docking interface, reports their own observations. Their perspective provides crucial additional information, since sensor packages on both vehicles offer different measurement capabilities. Their vibration sensors may detect subtleties invisible to your instrumentation. Their visual observations through viewports might reveal external clues unavailable from your position. This collaborative troubleshooting exemplifies the interdependent nature of space operations. Temperature becomes a critical factor in diagnosing the mechanical jam. The docking mechanism spans the boundary between spacecraft interiors and the vacuum of space, creating extreme thermal gradients across its components. Portions exposed directly to space might experience temperatures below -100 degrees Celsius, while adjacent sections connected to pressurized interiors remain near 20 degrees Celsius. These differences cause materials to contract and expand at varying rates, potentially creating binding points where components press against each other with forces exceeding motor capabilities. Your displays show temperature sensor readings from multiple points across the mechanism. The pattern reveals significant thermal differentials coinciding with the rotation stoppage point. The exposed portions of the ring currently face deep space shadow, while the interior segments connect to your module's warm pressure vessel. This temperature mapping suggests thermal binding as a primary candidate for the malfunction source. The thermal management systems on both spacecraft offer potential solutions. By adjusting heating elements and coolant flows, controllers can attempt to equalize temperatures across the mechanism. This process requires patience, as heat transfers relatively slowly through the specialized materials designed specifically to minimize thermal conductivity between spacecraft exterior and interior environments. While thermal adjustments begin, mission planners consider more interventional options. The docking mechanism includes manual override capabilities, accessible from both vehicles. Using these systems requires physical access to interfaces located near the hatch area. The procedure involves removing access panels, inserting specialized tools, and applying carefully calculated torque directly to drive shafts. This approach carries its own risks, potentially causing damage if excessive force encounters legitimate mechanical obstructions rather than simple binding. The sensory experience inside your module shifts as thermal management adjustments take effect. Slight temperature changes become noticeable on surfaces near the docking interface. The familiar cabin scent alters subtly as heaters activate components that normally remain passive. The background acoustic signature changes as pumps adjust coolant flow rates through radiator systems. These environmental shifts provide tacit confirmation of ongoing recovery efforts even before mechanism response occurs. Minutes extend uncomfortably as temperature adjustments gradually propagate through the mechanical assembly. Your displays show thermal gradients slowly equalizing across the problem area. Position sensors continue reporting the same stored configuration, offering no indication of improvement despite these efforts. The waiting creates a unique form of stress, different from immediate crisis, but equally taxing as uncertainty persists without clear resolution timeline. Mission Control consults with engineering teams analyzing the telemetry. Their discussion reaching you through communication channels reveals the depth of contingency planning behind spacecraft operations. They reference similar incidents from previous missions, analyze material properties under current conditions, and calculate force tolerances for various intervention options. Their methodical approach balances urgency against risk, seeking solutions that resolve the immediate problem without creating cascading complications. The first sign of progress arrives subtly. Vibration sensors detect minute movement too small for position indicators to register. The capture ring remains officially at 37 degrees rotation, but accelerometers show microscopic shifts indicating binding forces have begun yielding to thermal equalization. This data provides crucial validation for the current approach while suggesting patience rather than escalation to more invasive procedures. Your body registers the subtle changes in the surrounding environment as the situation evolves. Muscles that tensed unconsciously during the initial malfunction begin gradually relaxing as positive indicators accumulate. Breathing patterns that shallowed under stress slowly normalize. These physiological responses occur largely below conscious awareness, yet contribute significantly to operational endurance during extended anomaly resolution. The station crew reports additional observations from their perspective. They detect faint sounds transmitted through the structure, describing them as brief metallic ticks rather than the concerning grinding heard earlier. These acoustic signatures suggest components shifting as thermal expansion creates microscopic clearances at binding points. Their report provides confirmation beyond instrumented data, highlighting the irreplaceable value of human perception in space operations. The display finally shows movement. Position indicators register 38 degrees, then 39, as the mechanism hesitantly resumes operation. Torque measurements show decreasing resistance, confirming the jam is resolving rather than simply forcing through obstruction. The rotation continues with intermittent pauses, each shorter than the last, as remaining binding points yield to thermal equalization and driving force. This progressive resolution creates a distinctive sensory experience. Each incremental movement transmits vibration through the structure that you feel through contact points with the module. The sounds evolve from concerning friction noises to more reassuring mechanical engagement indicators. The rhythm of operation remains irregular compared to nominal function, but the direction of change clearly trends toward resolution rather than deterioration. The environmental response within your module reflects the mechanism's gradually improving condition. Systems that adjusted to assist thermal management begin returning toward nominal settings. Power consumption graphs on your displays show decreasing draw as drive motors encounter reducing resistance. The integrated vehicle status indicators transition from warning states to cautionary levels, their amber hues replacing the earlier red alerts. As rotation surpasses 60 degrees, the mechanism's behavior noticeably smooths. Movement becomes more continuous with fewer hesitations. Vibration characteristics shift from the irregular patterns of binding to the rhythmic signatures of normal operation. These changes confirm that the primary jam has resolved, though engineers will later analyze recorded data to identify the specific cause and implement design modifications for future missions. The capture ring finally completes its prescribed 90-degree rotation. Confirmation sensors register proper positioning, allowing subsequent steps in the docking sequence to proceed. Structural hooks fully engage, creating the rigid connection necessary for long-term vehicle integration. Pressure seals compress to specification, ensuring atmospheric integrity once hatches open. The indicators transition to green status, signifying successful resolution of the mechanical anomaly. This recovery represents a particular triumph of spacecraft design philosophy. The system encountered an abnormal condition, operated outside expected parameters, yet incorporated sufficient margin and redundancy to achieve functional success despite these challenges. The experience demonstrates why space systems include extensive fault tolerance and why procedures emphasize graduated response protocols rather than immediate escalation to high-risk interventions. Your own response to this resolution reveals the psychological dynamics of space operations. The relief arrives not as sudden release but as gradual relaxation tracking with mechanical improvement. Each positive indicator incrementally reduces stress levels until normal operational mindset returns. This measured emotional pattern reflects the training emphasis on maintaining consistent performance across both nominal and contingency situations. The physical sensation of a successfully completed docking sequence has distinctive characteristics. The previously separate vehicles now move as a single integrated structure. Vibrations transmit differently through the combined mass. Acoustic signatures alter as sound travels through newly connected pathways. Environmental systems begin their subtle harmonization with air circulation patterns adjusting to the expanded volume. These changes signal the transition from docking operation to successful completion. Mission Control acknowledges the successful resolution while already shifting focus to subsequent operations. Their communications reflect the continuous nature of space operations, where each completed task immediately yields to the next requirement. The resolved mechanical jam becomes another data point for engineering analysis rather than a lingering focus of operational attention. This forward-looking perspective maintains mission momentum through both successes and challenges. Your module has now physically joined the International Space Station through a complex sequence of mechanical interactions. The automated systems have performed their functions, overcoming thermal binding through designed accommodations and procedural interventions. But as preparations begin for opening hatches between vehicles, another operational scenario may become necessary. The potential for manual intervention remains present in space operations, particularly when automated systems encounter conditions beyond their design parameters. The next challenge might require direct human manipulation of controls, testing your ability to execute precise movements in the disorienting environment of microgravity. The transition from automated docking systems to potential manual operations introduces an entirely different set of challenges. As the hatch preparation sequence initiates, another anomaly indicator illuminates. A pressure sensor in the interface between vehicles shows irregular readings. Automated systems, detecting this abnormality, pause their operations pending human decision. Mission Control's voice comes through your headset with an instruction that transforms your role from systems monitor to direct operator. Prepare for manual override procedures. This transition shifts your sensory experience dramatically. Where previously you observed displays and monitored feedback, now your physical interaction with the spacecraft becomes primary. Your body, evolved through millions of years in Earth's consistent gravitational field, must perform precise movements in an environment where that fundamental force is effectively absent. The microgravity condition, clinically termed G-load 0, transforms every aspect of human movement and perception. The manual override panel requires accessing a protected compartment near the docking interface. Releasing your restraints, you push gently away from your station. This simple action produces complex motion, without friction to dampen momentum. Your body continues moving until contacting another surface. The sensation resembles swimming, but with air offering negligible resistance compared to water. Your trajectory requires mental calculation rather than intuitive adjustment. Arriving at the access panel, you must stabilize your position to perform detailed work. On Earth, simply standing provides a stable platform from which arms can manipulate objects. In microgravity, every action produces equal and opposite reaction. Turning a handle causes your body to rotate in the opposite direction. Pushing a button drives you backward unless counterbalanced. These Newtonian physics principles, intellectually familiar to every schoolchild, become viscerally challenging when personally experienced. The panel opens to reveal the manual override interface. This system intentionally uses mechanical rather than electronic controls for maximum reliability. A series of knobs, levers, and indicators allows direct human operation of critical mechanisms. Their design reflects decades of human factors research, with shapes and movements optimized for operation while wearing pressurized gloves if necessary. Each control requires specific force application along particular vectors, movements that on Earth would be straightforward but in microgravity become complex calculations. Your hand reaches for the primary override lever. On Earth, your arm would remain stable while only your hand moved. In orbit, your entire body becomes part of a connected system. Extending your arm shifts your center of mass, causing subtle rotation of your torso. This rotation must be mentally anticipated and physically counteracted to maintain position. The required bodily awareness resembles advanced yoga or martial arts training, a continuous full-body engagement rather than isolated limb movement. The lever requires 15 pounds of force to activate. On Earth, this resistance would provide helpful feedback and stability. In microgravity, applying 15 pounds of force to the lever means your body receives 15 pounds of force in the opposite direction. Without preparation, this would send you floating away from the control panel. Maintaining position requires bracing with your legs against adjacent structure, creating a temporary framework that redirects reaction forces through the vehicle rather than your floating body. Environmental factors complicate this physical challenge. The spacecraft maintains temperature within habitable range, yet thermal stratification occurs without convection currents driven by gravity. Some areas feel noticeably warmer or cooler than others. Humidity behaves similarly, creating pockets of varying moisture content that you pass through while moving through the cabin. These subtle atmospheric variations add another sensory layer to the operational environment. The recycled air carries that distinctive spacecraft scent, a combination of electronic components, filtered oxygen, material outgassing, and human presence. This olfactory signature remains consistent regardless of your position in the module, one of the few sensory constants in an environment where visual and tactile inputs constantly change with movement. The background sounds of environmental systems provide another constant, the mechanical heartbeat of life support that continues regardless of operational contingencies. Your fingers grasp the override lever, applying carefully calculated pressure. The mechanism resists initially, then yields with mechanical precision. Through your fingertips, you feel the internal components engaging, a series of detents and catches transferring your manual input into system operation. This direct mechanical connection provides immediate feedback unavailable through computerized interfaces. The tactile sensation confirms successful activation before visual indicators update. The physical operation of manual controls in microgravity requires specific techniques unlike terrestrial experience. Movements must be deliberate rather than quick. Forces need application along precise vectors. Body position requires constant management through subtle adjustments. The experience resembles delicate underwater work but without water's dampening effect on momentum. Each action must consider not just its primary purpose but all secondary effects across your floating body. Your displays confirm the manual override has successfully engaged. The pressure sensor that showed anomalous readings now bypasses primary systems, allowing the hatch sequence to continue under manual control. This transition represents a fundamental philosophical element of spacecraft design, where automated systems handle nominal operations but human intervention capability remains for situations requiring judgment and adaptability beyond programmed parameters. The manual sequence requires coordinated operation of multiple controls. Each step must occur in precise order with confirmation before proceeding. Unlike automated sequences that execute at electronic speeds, this operation proceeds at human pace. Your movements between controls follow arcing trajectories rather than direct paths, as momentum carries your body through the microgravity environment. These movements require constant mental calculation to arrive precisely where needed without overshooting or collision. Physical adaptation to microgravity affects your performance during these operations. Blood redistribution changes cerebral pressure, subtly affecting cognitive function and visual acuity. Muscle memory calibrated for terrestrial operation requires continuous conscious override. The vestibular system, which normally integrates motion and orientation information, receives conflicting inputs without gravity's reference point. These physiological factors compound the mechanical challenges of manual operation. The next step requires simultaneous activation of two widely separated controls, a safety feature preventing accidental operation. On Earth, this would simply involve using both hands. In microgravity, positioning your body to reach both controls while maintaining stability introduces complex biomechanical calculations. You brace one foot under a floor handhold, positioning your body in a modified version of what would be a push-up position on Earth. This orientation allows reaching both controls while managing reaction forces through your braced foot. Your muscles work differently in this environment. Without gravity constantly loading the body, muscular engagement becomes primarily about positioning rather than support. Smaller, finer muscle groups often take precedence over the large power muscles that dominate terrestrial movement. The proprioceptive system, which tracks body position through internal sensors, continuously recalibrates for this unusual loading pattern. After extended time in orbit, this adaptation becomes semi-automatic, but still requires conscious attention during precision tasks. The manual operation continues with careful activation of remaining controls. Each successful step produces specific feedback, both through mechanical sensation and updated display indicators. The procedure advances methodically toward completion, transforming potential mission compromise into manageable contingency. Your training for these scenarios, conducted in neutral buoyancy facilities and virtual reality simulators on Earth, now translates into effective performance despite the alien operational environment. Microgravity introduces unique fatigue patterns during extended manual operations. Muscles unaccustomed to continuous positioning work tire differently than during Earth activities. Blood pools differently in the body, affecting stamina and concentration. Thermal regulation operates without convective assistance, sometimes creating localized heating that further impacts performance. These factors influence the pace of manual procedures, requiring periodic micro breaks to maintain precision throughout extended sequences. The final control activation completes the override procedure. System indicators confirm successful transition to nominal operation despite the sensor anomaly that triggered manual intervention. The pressure equalization sequence resumes, now under careful human monitoring rather than fully automated control. This hybrid operation mode exemplifies modern spacecraft design philosophy, blending automation with human oversight and intervention capability. The physical experience of successfully completing manual override procedures carries distinct satisfaction. The direct connection between your actions and system response creates immediate feedback unavailable through automated operations. The knowledge that human adaptability resolved a situation that stymied pre-programmed systems reinforces the value of crewed spaceflight, despite its substantial challenges and costs. This operational success through manual intervention becomes part of both mission documentation and personal experience. Returning to your primary station requires another set of carefully calculated movements through the microgravity environment. Rather than simply walking back, you project yourself along a planned trajectory, using gentle pushes against structure to guide your floating transit. Arriving at your station, you engage restraints that secure your position without the assistance of gravity. These movements, alien on Earth, have become second nature through training and orbital experience. Mission Control acknowledges the successful manual intervention with professional appreciation in their communications. Their perspective from Earth observed the procedure only through telemetry in your verbal reports, a limited window into the physical reality you experienced. Their confirmation of procedure completion and system restoration adds official validation to your direct operational awareness. The environmental systems continue their subtle background processes throughout these operations. Air circulation fans maintain gentle flow that prevents carbon dioxide concentration around stationary crew. Temperature control systems respond to changing heat loads as equipment activates and deactivates. Humidity management captures and processes moisture from breath and perspiration. These automatic functions continue regardless of the manual contingencies occurring simultaneously, maintaining the life support envelope that makes human presence possible. With the pressure equalization sequence back on track, preparations for hatch opening continue. The direct manual operation transitions back to supervisory monitoring as automated systems resume normal function. Your role shifts accordingly, from physical manipulation of controls to vigilant observation of indicators. This operational flexibility, transitioning between automatic and manual modes as situations require, exemplifies the complementary capabilities of human and machine in complex space systems. The sensory experience changes subtly with this role transition. Physical engagement decreases as mental monitoring increases. Your body, having adjusted to the active movement requirements of manual operation, now must readapt to the primarily stationary observation position. This transition itself requires managed adaptation, as muscles that tensed for precise control now need to relax appropriately, without the normal settling effect of gravity. The hatch operation sequence continues toward completion, the earlier anomaly resolved through manual intervention. But this successful resolution hints at yet another challenge lurking within the complex physics of orbital operations. As systems reconnect and energy transfers between the previously separate vehicles, subtle vibrations begin propagating through the structure. These oscillations, barely perceptible initially, suggest the onset of a phenomenon that has concerned spacecraft engineers since the earliest days of orbital assembly: structural resonance, where mechanical energy finds harmonic frequencies within the connected vehicles and amplifies with potentially destructive consequences. The initial indication comes not through instrumentation, but through your own senses. A subtle vibration transmits through your fingertips where they rest on the control panel. The sensation resembles a distant bass note, felt rather than heard, a rhythmic pulsation traveling through the spacecraft's aluminum structure. Your eyes move to the accelerometer display, confirming what your body already detected. Vibration amplitude readings show a small but consistent oscillation at 4.7 Hz, a frequency that raises immediate concern among experienced spacecraft operators. Structural resonance represents one of the most insidious dangers in orbital assembly operations. Unlike obvious failures with clear indicators, resonance builds gradually as harmonic vibrations find matching frequencies within complex structures. The International Space Station, assembled from modules launched over decades, contains hundreds of potential resonant frequencies. When external forces match these natural harmonics, vibration can amplify dramatically, like pushing a playground swing with perfectly timed inputs. The source of the initial vibration appears to be the thermal control system in your recently docked module. As radiator pumps cycle fluid through external panels, their mechanical operation transmits subtle forces into the structure. Under normal circumstances, these forces dissipate harmlessly, but the particular frequency of this pump's operation happens to align with the harmonic frequency of a truss element connecting to the station's solar arrays, creating an amplification pathway with potentially serious consequences. The physical sensation evolves as resonance begins building. What started as barely perceptible vibration grows more pronounced. The frequency remains constant while amplitude gradually increases. Through the structure you feel the oscillation strengthening, transmitting through your seat restraints and control interfaces. The sensation resembles sitting in a vehicle with an out-of-balance wheel, a rhythmic disturbance that penetrates awareness despite attempts to ignore it. Mission Control registers the anomaly through telemetry feeds. Their communication reflects increasing concern as data analysis reveals the resonant pattern developing across structural elements. Their voice maintains professional calm while conveying urgency, requesting additional sensor activations to better characterize the vibration distribution throughout the combined structure. This data will guide intervention strategies to dampen the oscillation before amplitude reaches damaging levels. The sound of resonance adds another sensory dimension to the experience. Initially below audible threshold, the vibration frequency gradually enters perceptible range as amplitude increases. The result creates a disturbing hum that permeates the module, seemingly coming from everywhere at once. This sound has distinctive psychological impact, its persistence and omnidirectional nature making it impossible to localize or ignore, adding subtle stress that compounds the technical concerns. Visual evidence of resonance appears as minute trembling in loosely secured items. A water droplet floating mid-cabin begins oscillating in place, its surface tension deforming in rhythm with the structural vibration. Flexible elements like cable bundles show slight movement synchronized to the resonant frequency. Through exterior viewports, the station's solar arrays show concerning deflection patterns, their massive panels flexing visibly with each oscillation cycle. The station crew reports additional observations from their positions throughout the structure. Different modules experience varying vibration amplitudes depending on their position relative to resonance nodes. Some areas feel relatively stable while others encounter pronounced effects. This distributed information helps engineers map the resonance pattern across the entire station, identifying both the amplification pathways and potential intervention points. Your body's physiological response to sustained vibration creates another operational consideration. Prolonged exposure to certain frequencies affects fine motor control precision. Visual acuity can deteriorate slightly, as ocular stabilization systems contend with vibrating reference points. Vestibular sensitivity increases, sometimes producing mild disorientation similar to motion sickness. These human factors influence both immediate performance and longer-term tolerance if resonance continues. Environmental systems show subtle reactions to the vibration. Air circulation patterns develop minute variations as fan operation interacts with structural movement. Loose items gradually migrate towards structure nodes through a process resembling mechanical sorting. The background soundtrack of equipment operation takes on slightly modified tones as vibration affects moving components. These environmental changes provide additional sensory indicators of the resonance phenomenon beyond direct structural feedback. The resonance management procedures activate quickly once the pattern becomes evident. The primary intervention involves altering the frequency characteristics of the initiating systems. Engineers command your module's thermal pumps to adjust operating parameters, shifting their cycling frequency away from structural harmonic values. This adjustment requires careful calibration, as simply changing speeds could potentially match different resonant frequencies if not properly calculated. Secondary countermeasures involve activating the station's attitude control system in a specialized damping mode. This procedure uses the control moment gyroscopes and reaction control thrusters to create precisely timed counterforces that interrupt the resonant pattern. Like counter-noise headphones producing inverse sound waves to cancel ambient noise, these forces generate opposing motion vectors specifically designed to disrupt harmonic buildup. The sensation of these interventions creates a distinct physical experience. The original resonant vibration maintains its frequency but begins fluctuating in amplitude as countermeasures interact with established patterns. The feeling resembles listening to two similar musical notes producing beat frequencies as they interact. Through your fingertips and body contact points you feel this complex interplay of forces as systems work to regain structural equilibrium. The potential consequences of unchecked resonance lend urgency to these interventions. Historical examples from aerospace engineering demonstrate how devastating harmonic vibration can become. Bridges have collapsed, aircraft wings have failed, and early spacecraft structures have been damaged through resonance effects. The space station, with its extended solar arrays, radiator panels and multi-segmented design, contains numerous components vulnerable to these phenomena if vibration amplitudes exceed design tolerances. Your module's control systems provide feedback on the ongoing damping efforts. Displays show vibration amplitude gradually decreasing at most measurement points as interventions take effect. The reduction follows non-linear patterns, sometimes temporarily increasing before resuming decline as complex wave interactions work through the structure. This unintuitive behavior highlights why automated systems alone cannot fully address resonance situations without human monitoring and adjustment. The audio signature of diminishing resonance creates a satisfying sensory confirmation of improving conditions. The pervasive hum gradually fades below audible threshold as vibration amplitudes decrease. This audio reduction provides psychological relief alongside technical reassurance, removing the stressful sensory input that accompanied the developing anomaly. The cabin returns to its normal acoustic environment of circulation fans, equipment operation, and occasional communications. Mission Control coordinates additional preventative measures across the station's systems. Scheduling adjustments ensure that equipment operations with potential vibrational impact avoid simultaneous activation. Sensor thresholds receive updated parameters to provide earlier warning of developing resonance patterns. These systemic changes represent the organizational learning process that follows each anomaly, continuously improving operational safety margins based on experience. The physical sensation when resonance finally diminishes below significant levels brings noticeable relief. Your body, which tensed unconsciously during the event, gradually relaxes as vibration ceases. Muscle groups particularly responsive to the specific frequency range release their protective contraction. Even breathing patterns, which subtly synchronize to the vibration rhythm, return to normal cadence. These physiological responses occur largely below conscious awareness, yet significantly affect overall condition. The entire resonance event, from initial detection to successful damping, demonstrates the integrated nature of human and machine systems in space operations. Instrumentation provided precise measurements while human perception offered immediate detection and qualitative assessment. Computer systems executed damping algorithms, while human operators adjusted parameters based on observed effectiveness. This complementary capability exemplifies why crewed missions maintain advantages over fully automated systems for complex operational scenarios. Throughout the resonance management operations, normal mission activities continued in parallel. Life support systems maintained appropriate atmospheric conditions. Communication networks transmitted critical data. Power generation and distribution systems provided necessary electrical supply. This operational continuity highlights the robust design philosophy of space systems, where multiple challenges can be addressed simultaneously without compromising fundamental functions. With structural stability restored, attention returns to completing the docking operations interrupted by these successive anomalies. The pressure equalization process is completed during resonance management, allowing final preparations for hatch opening. System indicators show appropriate pressure matching between vehicles, temperature equalization across the interface, and atmospheric composition within compatible parameters. These conditions clear the way for physical connection between internal environments. The experience of these compounding challenges, mechanical jams, manual intervention requirements, and structural resonance, demonstrates why orbital docking operations remain among the most demanding aspects of space missions, despite decades of engineering development. Each successful resolution introduces new appreciation for the complexity involved in joining separate spacecraft traveling at orbital velocity. The process represents not just technical achievement, but the accumulated knowledge from previous failures and near misses throughout spaceflight history. As final hatch preparation procedures continue, your attention momentarily shifts to the exterior environment surrounding your joined spacecraft. Through the viewport, Earth's blue horizon curves against the black backdrop of space. This stunning vista provides momentary perspective on the technical challenges just overcome. But within that seemingly empty blackness lurks another category of hazard that haunts every orbital operation, invisible until moment of impact yet potentially catastrophic in consequence: orbital debris. The silent population of human-made and natural objects that share the orbital environment with operational spacecraft. The radar tracking system activates without warning. A distinctive alert tone fills the module, drawing your attention immediately to the threat display. The screen shows a tracked object approaching your docked configuration at relative velocity of 25,000 miles per hour. The projected miss distance calculates to 143 feet, uncomfortably close by orbital standards, but outside the typical debris avoidance threshold. The object measures approximately 2 centimeters diameter, likely a fragment from a previous satellite breakup event. Small enough to escape ground-based tracking networks, yet large enough to catastrophically damage spacecraft if impact occurs. This moment dramatically shifts your sensory focus. The spacecraft interior, which had dominated your attention during docking operations, suddenly feels thin and vulnerable. The few inches of aluminum and composite materials separating you from vacuum take on new significance when considered as protection against hypervelocity impacts. The environmental systems continue their steady operation, maintaining living conditions with the same quiet efficiency as before the alert, yet your perception of their fragility fundamentally changes. Orbital debris represents one of the most insidious threats to space operations. The low Earth orbit environment contains millions of objects created through human space activities spanning decades. Spent rocket stages, defunct satellites, fragments from collisions and explosions, even paint flakes and frozen coolant droplets orbit at velocities where even the smallest objects carry enormous kinetic energy. A 1 centimeter paint chip traveling at orbital velocity impacts with force comparable to a bowling ball moving at 60 miles per hour. The tracking display updates as the debris object approaches. Uncertainty ellipses around its projected path, shrink as radar returns provide improved position data. The miss distance recalculates to 128 feet, still outside immediate danger parameters, but trending in concerning direction. Mission Control acknowledges the tracking alert, confirming they monitor the same object from ground systems. Their voice maintains professional calm while conveying appropriate urgency, balancing the competing needs of prompt response without undue alarm. Your body responds involuntarily to this potential threat. Respiration rate increases slightly. Heart rate elevates measurably. Peripheral vision expands in an evolutionary response designed to detect movement, despite the intellectual understanding that you cannot visually detect the approaching object. These physiological changes happen automatically, part of the human threat response system that operates below conscious control. The International Space Station incorporates specific protective measures against the debris environment. Whipple shields, consisting of thin outer layers separated from pressure hulls, provide protection against smaller particles. These shields work through physics rather than strength, using initial impact to vaporize projectiles into gas clouds that disperse energy before reaching critical structures. Critical components receive additional shielding, while the station's modular design includes pressure isolation capabilities to contain potential breaches. The distinctive features of orbital debris threats create unique psychological impacts. Unlike most dangers that provide sensory warning before impact, space debris strikes without perceivable approach. The first indication of collision would be the impact itself. This characteristic creates a threat profile that human psychology finds particularly unsettling, similar to the unique stress of tornado warnings or tsunami alerts where danger might or might not materialize with little intermediate indication. Through the viewport, you see only the star field and Earth's illuminated curve. The approaching debris remains invisible, too small for optical detection, despite its destructive potential. This sensory disconnect, where the most sensitive instruments detect threats completely imperceptible to human senses, exemplifies the alien nature of orbital operations. Evolution prepared human threat response for predators and environmental dangers, not hypervelocity particles moving in perfect vacuum. The tracking system continues updating projected trajectories. The missed distance recalculates again to 117 feet, maintaining the slow trend toward closer approach but still outside immediate danger parameters. The time to closest approach shows 4 minutes remaining. This countdown creates measurable tension, the awareness of approaching potential danger combined with complete inability to physically perceive or directly respond to the threat. Station procedures for debris events follow carefully designed protocols based on threat parameters. For objects with sufficient warning and concerning trajectories, the primary response involves maneuvering the entire station using thrusters to increase miss distance. This procedure requires significant advance notice due to the station's massive size. For threats detected too late for maneuvering, procedures shift to crew sheltering in the most protected modules, typically Soyuz or Crew Dragon vehicles that could serve as emergency return craft if necessary. The current alert level falls between these response categories. The projected missed distance remains outside the threshold requiring immediate action, yet close enough to justify enhanced monitoring. This intermediate state creates its own form of stress, the uncertainty of balanced probabilities rather than clear procedural response. Experience demonstrates that tracking uncertainties occasionally result in closer passages than initially projected, justifying continued vigilance despite apparently safe parameters. Your attention divides between monitoring approach displays and continuing necessary docking operations. This cognitive multitasking represents another challenging aspect of orbital operations, where multiple critical activities often require simultaneous attention. The environmental systems continue circulating air, managing temperature, and processing carbon dioxide. The docking mechanism continues its post-capture securing procedures. Background communications between various control centers discuss both the debris tracking and nominal operations. All these activities proceed in parallel despite the potential threat approaching at orbital velocity. The sensory environment inside the module provides stark contrast to the external danger. Air circulation creates gentle background sounds. Temperature control maintains comfortable conditions. Lighting provides consistent illumination across work surfaces. These environmental constants continue unchanged while instruments track an object that, if its path shifted slightly, could catastrophically compromise this entire life-supporting envelope in milliseconds. This juxtaposition of ordinary conditions with extraordinary threat creates a distinctive psychological experience unique to spaceflight operations. The tracking display shows the debris object entering its final approach minute. Position uncertainty has reduced with additional radar returns, providing increased confidence in the projected trajectory. The missed distance has stabilized at 112 feet, maintaining comfortable margin outside the 70-foot critical threshold that would trigger emergency procedures. The time to closest approach counter decreases steadily, creating a focused point of attention that seems to compress subjective time perception. Your body continues its subtle stress response throughout the tracking event. Muscle groups across shoulders and neck maintain slight tension in evolutionary preparation for physical response, despite the intellectual understanding that no direct action can affect the outcome. Breathing unconsciously shallows, an autonomic response to perceived threat. These physiological changes happen despite training and experience, demonstrating how deeply embedded survival responses remain even in environments completely unlike those that shaped human evolution. The moment of closest approach arrives without physical sensation. The debris passes your position at relative velocity that would cross the entire length of a football field in 1 millisecond. The tracking display shows position history changing from approaching vectors to receding trajectories. The moment itself feels strangely anticlimactic, marked only by instrument indications rather than direct perception. The miss distance finalizes at 108 feet within expected parameters given initial tracking uncertainties. Mission Control confirms the successful tracking and passage of the debris object. Their communication carries subtle relief while maintaining professional tone. Ground systems will continue monitoring the object's trajectory as standard procedure, ensuring it poses no future threat through orbital interactions. The event transitions from active concern to historical documentation, joining the thousands of similar close approaches recorded throughout the station's operational lifetime. The psychological aftermath of the debris encounter follows a distinct pattern. The immediate relief of successful passage gradually yields to renewed awareness of the continuous nature of this threat. Unlike discrete events with clear beginning and conclusion, the orbital debris environment represents a persistent hazard field through which spacecraft constantly travel. Each tracked object successfully avoided implies countless others too small for detection yet potentially damaging if encountered. This near-miss event carries educational value despite its ultimately benign outcome. The tracking data collected will improve debris modeling algorithms. Response procedures receive real-world validation. Crew experience with the scenario enhances future preparedness. These learning opportunities transform potential threats into operational improvements, a pattern repeated throughout spaceflight history, where close calls become valuable experience rather than merely avoided disasters. The environmental systems inside your module register subtle changes corresponding to your physiological response during the tracking event. Carbon dioxide sensors detect slightly elevated output from increased respiration. Temperature sensors register minor increases in localized readings near crew positions. Humidity management processes additional moisture from stress-induced perspiration. These small variations illustrate the intimate connection between human occupants and life support systems, each responding to and influencing the other. With the debris threat receding behind your position, attention fully returns to completing docking operations. The hatch preparation procedures resume their methodical sequence, pressure equalization complete and mechanical interfaces secured. Display indicators show all systems ready for hatch opening, the physical connection between spacecraft atmospheres that represents the final step in vehicle integration. Mission timelines adjust slightly to accommodate the brief focus on debris tracking, demonstrating the operational flexibility built into procedures. The station's regular orbit carries you towards sunrise, one of 16 such transitions experienced during each 24-hour period. Through viewports, the approaching terminator appears as brightening blue curve along Earth's edge. This imminent lighting change holds practical significance beyond its visual beauty. Solar illumination will soon flood areas previously in darkness, including the recently docked interface. This lighting transition allows visual inspection of external mechanisms not fully visible during night passage. As sunlight reaches your position, the exterior view transforms dramatically. Surfaces previously hidden in shadow reveal their details. The docking mechanism catches this angled illumination, showing secure connection without visible anomalies. This visual confirmation supplements instrument readings with direct observation, providing additional confidence in docking integrity. The natural lighting also reveals the broader orbital environment, including distant structural elements that should be monitored during initial pressurization changes. The experience of this debris tracking event, though ultimately uneventful in outcome, leaves lasting impression about the operational environment of low Earth orbit. The natural void of space, seemingly empty to casual observation, actually contains an artificial ecology of human-created objects orbiting at extreme velocities. This environment, invisible to direct perception yet constantly monitored by sophisticated sensors, represents one of the unique challenges of orbital operations that distinguishes spaceflight from all other human activities. As procedures advance toward hatch opening, thoughts of debris hazards remain present but appropriately contextualized within the broader risk profile of space operations. The successful tracking and passage of this particular object reinforces confidence in detection systems while maintaining realistic awareness of their limitations. This balanced perspective, neither dismissive of genuine threats nor paralyzed by their continuous possibility, characterizes the professional approach to hazard management in orbital operations. The next phase of docking completion involves final pressurization adjustments and hatch release preparations. But system checks reveal an unexpected pressure differential that exceeds normal parameters despite equalization procedures. This anomaly triggers automated safety protocols, initiating a sequence that dramatically alters the docking timeline. Warning indicators illuminate across your control panel as the system prepares for a contingency procedure that all crews train for extensively but hope never to experience: the emergency abort sequence, where vehicles must quickly separate to prevent escalating problems from threatening both spacecraft. The first indication comes through an unmistakable audio alert, 3 short tones repeated at half-second intervals. Your eyes instantly move to the master alarm display, where a red warning indicator confirms dock abort sequence initiated. Internal pressure readings between the spacecraft show unexpected increases approaching safety limits. Time compression descends immediately, transforming each second into a complex decision space filled with potential consequences. The automated systems have detected conditions warranting emergency separation, but final execution awaits your confirmation within the next 30 seconds. The sensory experience transforms instantly with this emergency declaration. Background sounds that had faded from conscious awareness now disappear entirely as attention tunnels to critical indicators. The recycled air seems suddenly thinner though oxygen levels remain unchanged. Your field of vision narrows to essential displays, peripheral awareness diminishing as cognitive resources redirect to emergency response. A metallic taste appears in your mouth, the body's autonomic stress response elevating in perfect synchronization with the situation's urgency. Abort sequences represent the emergency escape path from deteriorating docking operations. Designed as the last resort protection against catastrophic failures, these procedures prioritize spacecraft separation above all other considerations. The philosophy acknowledges that two intact independent vehicles represent a better outcome than two vessels potentially compromised by continued problematic connection. The procedure accepts significant operational penalties to ensure physical safety margins. Your displays show the specific abort trigger. Pressure increases in the docking interface, suggesting potential leak paths developing between sealing surfaces. The rate of pressure change exceeds allowable limits by 17%, with trend lines showing continued deterioration. This specific failure mode suggests mechanical misalignment, allowing atmosphere to infiltrate spaces designed to remain at vacuum until final hatch opening. While not immediately dangerous, this pattern typically precedes more serious seal failures if connection maintains. Mission Control acknowledges the abort initiation with terse professional communication. Their voice maintains measured cadence despite the emergency situation, a deliberate technique to promote calm decision-making. Their systems mirror your telemetry, showing the same concerning pressure trends from ground perspective. They confirm abort recommendation based on established flight rules while acknowledging the final decision remains with on-scene command according to contingency authority protocols. The physical preparation for abort execution creates distinct sensory experiences. Your hands move to designated control positions through trained muscle memory rather than conscious direction. Fingers find specific switches and guards without visual confirmation, tactile pathways established through hundreds of simulation repetitions. Your body subtly braces against restraints, anticipating the coming acceleration when separation thrusters activate. Breathing patterns shift automatically to the controlled rhythm practiced for high-stress operations. The abort sequence display shows the automated checklist progressing through initial stages. Systems verify proper configuration for emergency separation. Docking mechanism latches prepare for rapid release. Thruster systems pressurize to maximum availability. Power connections between vehicles prepare for immediate disconnection. Each green confirmation indicator represents a system ready for the coordinated separation about to occur, building toward the final command that will physically divide the recently joined spacecraft. Time continues its subjective distortion throughout the emergency sequence. The 30-second decision window seems simultaneously too brief for proper analysis, yet agonizingly extended through moment-by-moment awareness. Each passing increment decreases available options while increasing pressure for final determination. This temporal distortion represents a well-documented psychological phenomenon during emergency operations, where perception adapts to crisis demands through altered subjective experience. The station crew receives simultaneous notifications about the pending abort. Their communications acknowledge the situation while confirming their own emergency preparations. Internal hatches close to isolate potential pressure issues. Station systems reconfigure for independent operation following separation. Their perspective from the opposite side of the docking interface provides complementary data confirming the anomalous pressure readings that triggered the abort sequence. Your decision process works through the emergency response algorithms ingrained through training. The displayed data meets multiple abort criteria without ambiguity. The trend lines show continuing degradation rather than stabilization. Alternative explanations for the sensor readings have been eliminated through secondary confirmations. The risk assessment for continued docking exceeds acceptable parameters by significant margins. These analytical pathways converge toward the only justified conclusion despite its operational impact. Your finger presses the abort confirmation control with deliberate pressure. The tactile feedback of the switch engagement creates a distinct sensation, the physical commitment to emergency separation. The system responds immediately, status indicators changing from amber pending notifications to red execution confirmations. The automated sequence transitions from preparation to active implementation, now committed to complete separation regardless of subsequent developments. The first physical indication of abort execution comes through vibration transmitted through the structure. The docking mechanism hooks disengage simultaneously, releasing the rigid connection between vehicles. This disengagement produces a distinctive sound resembling multiple deadbolts retracting in rapid sequence. The sensation travels through the module structure into your body through contact points with restraints and control interfaces, a mechanical communication of systems in motion. Next comes the more substantial physical experience as separation thrusters activate. The initial pulse pushes you gently against your restraints as acceleration forces build. Unlike the dramatic launches depicted in entertainment media, this separation occurs with precisely calculated minimum forces required to achieve safe distance within appropriate timelines. The acceleration feels firm but manageable, approximately 1/10 Earth gravity sustained for several seconds rather than violent impulse. Visual confirmation of separation appears through viewport and camera displays. The distance between your module and the station begins increasing at approximately 2 feet per second, a pace that appears deceptively slow given the emergency nature of the maneuver. This carefully controlled separation rate balances competing requirements, moving away quickly enough to prevent potential damage propagation while avoiding excessive velocity that could complicate subsequent operations. The sound signature inside your module changes noticeably during separation. The background noise of shared environmental systems gives way to the more familiar acoustic pattern of your individual spacecraft. Thruster activations create periodic rumbles transmitted through the structure. Air circulation systems adjust to the reconfigured volume, creating subtle changes in flow patterns and associated sounds. These audio cues provide confirmation of successful separation as compelling as visual indicators. Communication systems maintain connection despite physical separation, allowing continued coordination between vehicles. The professional terminology shifts to reflect the changed situation, with position reports now referencing separation distance and relative vectors rather than docking interface parameters. This linguistic adjustment reinforces the operational reality of having transitioned from joined configuration back to independent vehicles maneuvering in proximity. Your displays show the abort sequence progressing through subsequent phases. After initial separation achieves sufficient clearance, thrusters execute a secondary burn establishing departure trajectory. This maneuver increases separation rate while establishing orbital parameters that prevent unexpected close approaches in subsequent orbits. The guidance system calculates this trajectory considering the complex orbital mechanics of objects traveling at 17,500 miles per hour, while separated by increasingly greater distances. The environmental systems respond to reconfiguration requirements following separation. Pressure control adjusts to the independent volume rather than shared spacecraft atmosphere. Thermal management adapts to changed heat load profiles without the station's contributions. Carbon dioxide scrubbing systems recalibrate for the smaller crew complement. These automatic adjustments maintain life support parameters within nominal ranges despite the operational transition. Mission control communication shifts to recovery operations as the abort sequence completes its critical phases. Their focus moves from immediate separation management to establishing revised mission timelines and approach opportunities. The professional tone acknowledges the setback while immediately pivoting toward solution development, exemplifying the operational resilience that characterizes successful space programs. Failure becomes temporary state rather than mission endpoint. The physical separation continues increasing, now measurable in hundreds of feet rather than inches. Through the viewport, the station appears as a complete structure again, rather than the intimate close-up view during docking. This visual perspective reinforces the psychological transition back to independent operations. Your module, recently integrated with the massive complex, returns to its identity as a separate spacecraft with its own operational parameters and requirements. Post-abort analysis begins immediately, even as separation continues. The telemetry recorded during the anomalous pressure events undergoes detailed examination seeking root causes. Engineers evaluate multiple potential failure modes including mechanical misalignment, thermal expansion effects, and control system timing issues. This analysis serves both immediate needs for planning potential reattempts and longer-term requirements for procedure and hardware improvements. Your body gradually registers the transition out of emergency response state. Muscles that tensed in preparation for potential physical demands slowly relax as separation proceeds without incident. Breathing patterns that shallowed during intense concentration return toward normal depth and rhythm. Heart rate decreases from elevated emergency levels, though remaining above baseline due to continued operational focus. These physiological adjustments mirror the operational transition from critical emergency to managed contingency. Mission Control provides updated timeline projections for potential redocking attempts. The orbital mechanics dictate specific windows where approach becomes possible with acceptable propellant usage. The earliest opportunity would come approximately 28 hours later, after completing nearly 19 orbits that position both spacecraft favorably for rendezvous. This extended timeline allows thorough analysis of the abort causes while maintaining mission continuation options. The sensory experience inside your module evolves throughout the post-abort phase. Temperature and humidity subtly shift as environmental systems optimize for the current configuration rather than preparation for station integration. The ambient light changes character as your trajectory carries you through different orbital lighting conditions without the station's shadow effects. The recycled air seems fresher as circulation patterns optimize for the smaller volume after adapting toward the larger combined environment. Propellant usage accounting becomes a critical focus following the abort maneuvers. The separation sequence consumed resources planned for final approach adjustments, reducing margins for subsequent attempts. Displays show remaining quantities with updated projections for various mission scenarios. These calculations directly influence decision-making about reattempt timing and approach profiles, balancing operational desires against hard physical constraints of available resources. The psychological impact of an abort sequence creates complex responses that require professional management. The disappointment of interrupted mission objectives contends with satisfaction of successful emergency system performance. Concern about root causes balances against confidence in detection and response capabilities. Awareness of setback timeline implications competes with recognition that safety margins functioned exactly as designed. Integrating these conflicting elements requires the psychological resilience characteristic of experienced space operators. Communication with the station crew continues throughout the separation, maintaining operational coordination despite the physical distancing. Their perspective provides valuable additional information about the abort execution from the station side of the interface. Their systems recorded different aspects of the anomalous pressure behavior, offering complementary data for comprehensive understanding. This collaborative analysis represents the international partnership fundamental to station operations despite the temporary physical separation. As your module establishes its independent orbital trajectory, automated systems transition from abort execution to normal flight operations. Displays reconfigure to show standard orbital parameters rather than separation-specific indicators. Environmental systems complete their adjustment to independent configuration. Power management optimizes for current requirements rather than shared resource allocation. These transitions mark the formal completion of the abort sequence and resumption of standard spacecraft operation. The experience of an emergency abort, though operationally disappointing, provides invaluable practical validation of safety systems and procedures. The detection algorithms properly identified anomalous conditions. Decision protocols balanced automated response with human judgment. Mechanical systems executed precise separation under emergency conditions. These confirmed capabilities transform a mission setback into a successful demonstration of critical safety margins, a perspective essential to professional space operations. As separation distance exceeds 1 kilometer, direct visual observation of the station requires optical assistance. Through viewport-mounted binoculars, the structure appears as an elaborate geometric form against the Earth background, its solar arrays catching sunlight in distinctive reflection patterns. This visual transition completes the psychological shift from imminent docking completion to separated spacecraft status, established physical reality replacing the anticipated connection. The hours following abort execution bring progressive understanding of the underlying causes. Engineering analysis identifies a thermal expansion differential between docking mechanism components as the primary factor driving the pressure anomalies. The specific orbital lighting conditions during final approach created temperature gradients exceeding normal parameters, affecting seal compression patterns at the interface. This understanding allows procedural adjustments for subsequent attempts, turning temporary failure into future improvement. This abort experience, while challenging and disappointing in immediate operational terms, contains the essential elements that will enable eventual success. The very systems that detected problems and executed safe separation will, with appropriate adjustments, ultimately facilitate successful docking. The knowledge gained through this setback creates the foundation for the next attempt, demonstrating the fundamental principle that has driven space exploration since its beginning. Failure instructs success when properly analyzed and applied to future operations. The path forward becomes increasingly clear as analysis continues and recovery plans develop. The revised approach will incorporate modified thermal management procedures to prevent recurrence of the expansion differential that triggered the abort. Timing will align with more favorable orbital lighting conditions to reduce temperature extremes across the docking interface. These adaptations transform apparent failure into developmental progress, the essential learning cycle that advances space capabilities through operational experience. With recovery planning established and systems stabilized in independent configuration, attention turns toward execution of the revised approach timeline. The next docking opportunity, now approximately 26 hours away, represents not merely a repeated attempt but an improved operation incorporating lessons from the aborted sequence. This progressive improvement exemplifies the fundamental philosophy underlying successful space programs. Each operational experience, whether nominal or contingency, advances capabilities through applied learning and procedural evolution. 27 hours and 14 minutes after the emergency abort, your module again approaches the International Space Station. This time everything feels different. The recycled air carries the same filtered scent, the displays show identical readouts, and the gentle thruster pulses provide familiar feedback through the structure. Yet your perception has fundamentally transformed. Where the previous approach carried the confidence of routine, this attempt brings heightened awareness of potential complications. The abort experience has sharpened your senses to nuances previously overlooked, creating an almost preternatural attentiveness to system indicators and environmental cues. The visual acquisition of the station occurs at approximately 4 kilometers distance. Through the forward viewport it appears first as a bright point, distinguishable from background stars only by subtle structural features visible through magnification. As distance decreases, the cruciform shape resolves into recognizable modules, trusses, and solar arrays. This progressive visual clarification mirrors your mental transition from abstract mission parameters to imminent physical interaction with the massive structure growing steadily in your field of view. This approach incorporates specific modifications based on lessons from the aborted attempt. The rendezvous trajectory brings your module to the docking port during a planned orbital midnight, eliminating the thermal gradients that contributed to previous seal expansion issues. Environmental system settings maintain more conservative temperature differentials across the docking mechanism. These adjustments represent the practical application of experience, transforming previous complications into procedural improvements. The sensory experience during final approach carries heightened intensity after the prior abort. Each thruster firing registers not just as physical feedback, but as critical information about trajectory control. The displays showing closing distance and alignment parameters demand constant attention, their values instantly compared against both normal parameters and abort thresholds. The station's visual appearance through the viewport becomes subject to continuous cross-reference with instrument readings, seeking integrated confirmation of proper approach conditions. Mission control communications reflect similar intensity, their procedural call-outs delivered with precise timing and clarity, their perspective informed by both standard monitoring and specific awareness of previous complications provides complementary oversight to your direct observations. Their voice maintains professional tone while conveying appropriate urgency at key decision points. This balanced communication exemplifies the partnership between ground and orbital personnel that characterizes successful space operations. The physical sensation as distance drops below 100 meters becomes increasingly familiar, yet overlaid with new significance. The module responds to final approach thruster firings with gentle movements transmitted through the structure to your body. These tactile cues, once background sensations during routine operations, now register as critical feedback deserving conscious attention. Your hands hover near manual override controls, ready to intervene if automated systems repeat previous anomalies. Environmental systems maintain optimal conditions throughout the approach, their operation a reassuring constant amid operational intensity. Temperature control keeps the cabin at precisely 21 degrees Celsius despite equipment heat generation. Humidity management processes exhaled moisture to maintain 45% relative humidity. Carbon dioxide scrubbers keep concentrations below 4 millimeters of mercury. These life support functions continue their vital work regardless of mission phase, maintaining the habitable envelope that makes human presence possible. The station crew maintains communication throughout approach, their perspective providing valuable additional information from the target side of operations. Their observations include visual confirmation of approach alignment, status updates on docking port configuration, and readiness confirmations for capture procedures. Their participation completes the operational loop between your module, mission control, and destination, creating redundant verification pathways for critical parameters. As distance decreases below 50 meters, the approach corridor narrows considerably. Acceptable deviation from center line reduces to inches rather than feet. Your displays show position indicators overlaid with tolerance bands that visually shrink as proximity increases. The precision requirements at this phase explain why docking operations remain challenging, despite decades of operational experience. The fundamental physics of joining massive objects traveling at orbital velocity demands extraordinary precision regardless of technological advancement. The visual appearance of the docking port through cameras and viewports shows noticeable differences from previous attempt. Lighting conditions during this orbital night approach create more consistent illumination through artificial sources, rather than harsh solar contrasts. The alignment markers appear clearly defined without glare interference. The depth perception challenges remain, but with reduced visual distractions complicating distance assessment. These conditions represent another lesson applied from previous experience. Your body responds to the increasing precision demands with physiological changes largely below conscious awareness. Breathing automatically shallows to reduce subtle body movement that might affect hand control inputs. Heart rate elevates slightly, increasing blood flow to brain and muscle groups involved in potential emergency response. Pupillary dilation enhances visual sensitivity in the relatively dim lighting conditions. These automatic adaptations optimize human performance for the critical task without requiring active management. The closing velocity maintains strict adherence to approach parameters, holding steady at approximately 1/10 of a foot per second during final phase. This glacial pace transforms the last 30 feet into 5 minutes of intensely focused monitoring, where progress seems simultaneously imperceptible yet inexorable. The timeline extends further than typical human attention span naturally maintains, requiring trained concentration to prevent vigilance degradation during these critical moments. The station's massive structure now fills viewport completely, transformed from distant object to immersive environment. This visual perspective shift alters spatial perception, your module seemingly stationary while the station appears to move toward you. This illusion, though intellectually recognized as contrary to actual dynamics, nonetheless influences intuitive judgment. Training overcomes this perceptual challenge through reliance on instrument reference rather than visual impression for critical decisions. The final moments before contact create distinctive time distortion. Subjective experience seems to both accelerate through heightened awareness and decelerate through extended focus duration. Each second expands to contain multiple observation cycles across instruments and visual references. This perceptual phenomenon resembles athletic experiences of being in the zone where time perception alters to accommodate performance requirements. The effect disappears from memory almost immediately after occurrence, leaving only operational results rather than recollection of the altered experience. Contact occurs with the gentlest perceptible feedback, a subtle vibration transmitted through the structure that registers more as absence of movement than positive confirmation. The sensation resembles touching a solid surface after expecting continued motion, the cessation itself becoming the primary indicator. Display confirmations appear simultaneously, capture sensors registering successful initial connection. This moment represents the culmination of thousands of calculations, hundreds of thruster firings, and decades of engineering development. The soft capture indicators illuminate in sequence across your display, confirming progressive engagement of initial connection mechanisms. These preliminary attachments create tenuous but meaningful link between vehicles, sufficient to maintain position while allowing automated systems to adjust final alignment before hard capture. Each indicator transitions from amber processing status to green completion confirmation, building the verification chain that authorizes subsequent steps. The physical sensation of successful soft capture creates noticeable physiological response. Muscles that maintained readiness for potential intervention gradually release their subliminal tension. Breathing patterns that shallowed during intense concentration return toward normal depth and cadence. A subtle but distinct sense of accomplishment emerges, professional satisfaction at successful execution rather than emotional celebration. These internal experiences remain largely private, expressed outwardly only through minimal changes in communication patterns. Mission Control confirms successful soft capture from their telemetry perspective, their voice carrying the same measured approval that characterizes all operational communications. Their acknowledgement completes the verification loop, adding ground-based confirmation to direct observation and instrument indication. This procedural redundancy represents fundamental space operations philosophy, where critical events receive confirmation through multiple independent pathways before proceeding to subsequent steps. With soft capture confirmed, the hard capture sequence initiates. This process draws the docking mechanisms together with progressive force, creating rigid structural connection rather than preliminary alignment. The sensation transmits through the module as series of gentle tugs, each bringing the vehicles incrementally closer. Display indicators track hook engagement percentages, showing gradual progression toward complete connection. This methodical process transforms two separate spacecraft into integrated configuration with shared structural integrity. The sound signature during hard capture provides additional feedback channel. Each hook engagement produces distinctive mechanical click transmitted through structure. The pattern resembles progressive tightening sequence, individual components engaging in carefully orchestrated order rather than simultaneous activation. These audio cues supplement visual indicators, providing redundant confirmation through different sensory pathways. The final engagement produces slightly more substantial sound, signifying completion of structural connection. Environmental systems begin harmonization procedures following successful hard capture. Pressure equalization preparations configure valves for controlled atmosphere sharing between vehicles. Temperature differentials between modules receive active management to prevent condensation at interface points. These coordinated system adjustments prepare for eventual hatch opening while maintaining appropriate isolation until verification completes. Each step proceeds with deliberate pacing, prioritizing verification over expediency. The distinctive sensory experience following successful docking combines multiple elements into unique gestalt. The physical vibration characteristics change subtly as your module becomes integrated with station's larger mass. Background sounds alter as acoustic transmission paths connect previously separate environments. The perception of movement during orbital adjustments transforms as thrusters now manage combined configuration rather than independent vehicle. These changes occur below obvious awareness yet contribute to comprehensive environmental shift. Status displays confirm completion of hard capture sequence, all indicators showing green nominal conditions. The structural connection between vehicles has achieved specified torque values, compression forces, and alignment parameters. The sealed interface shows appropriate pressure integrity across all monitored segments. These technical confirmations translate into operational reality. Two previously independent spacecraft have become single integrated structure capable of sharing atmosphere, power, data, and human passage. The pressure equalization process begins with careful valve sequencing. Unlike the previous attempt where anomalous readings triggered abort sequence, this operation proceeds with nominal indicators throughout. The subtle sound of initial gas transfer creates barely perceptible background note as atmospheres begin mixing under controlled conditions. Pressure sensors show gradual convergence toward unified value, rates remaining within conservative limits throughout process. This critical phase represents significant hazard management, as pressure differentials contain substantial energy if released improperly. Your body registers the equalization process through minor physiological indicators. Ears occasionally detect subtle pressure changes similar to elevation adjustments on Earth, but considerably gentler. Sinus passages might experience momentary awareness of changing atmospheric pressure. These sensations remain well below discomfort threshold, noticeable primarily through focused attention rather than significant physical impact. The environmental systems manage these transitions specifically to minimize human physiological response. Communication with station crew increases as shared operations prepare for hatch opening. Their voices, previously separated by radio transmission only, will soon become direct acoustic interactions. This imminent transition creates subtle shift in communication patterns, terminology adapting toward in-person dynamics rather than radio protocols. The psychological preparation for direct human contact after isolated spacecraft operation begins well before physical connection occurs. The hatch preparation procedures initiate following pressure equalization completion. Mechanical interlocks verify proper configuration for opening operations. Indicator lights confirm atmospheric compatibility between modules. Final safety checks ensure all systems properly configured for integrated operations. These procedures transform sealed pressure vessels into connected habitable volumes, a transition requiring multiple verified safeguards given the critical life support implications. The physical sensation as the hatch finally opens creates the mission's defining moment. Air movement between modules generates slight breeze perceptible on exposed skin. The olfactory environment changes noticeably as atmospheres mix, bringing distinctive scents from station environment. The acoustic space expands dramatically as sound now travels between connected volumes rather than reflecting within confined module. These sensory changes arrive simultaneously, creating immediate and unmistakable confirmation of successful docking completion beyond any instrument indication. The station crew appears in the opened hatchway, their presence transforming abstract mission objectives into human reality. The professional handshakes and restrained greetings follow established protocols while carrying genuine significance beyond procedural requirements. This moment represents the fundamental purpose behind all technical challenges overcome during approach and docking, enabling human connection across the most extreme environment humans operate within. The environmental transition continues as you move from module to station. Temperature variations become noticeable between areas, some slightly warmer or cooler depending on equipment density and proximity to external surfaces. Humidity levels shift subtly between zones, reflecting different environmental control settings. Background sounds change continuously while moving through the complex, each module carrying distinctive acoustic signature from equipment configurations and structural resonance patterns. These environmental variations transform the previously monolithic concept of space station into nuanced, differentiated habitable space. Mission control communications acknowledge successful docking completion with appropriate procedural terminology, while conveying understated satisfaction with the achievement. Their perspective now transitions from critical operational oversight toward support role for subsequent activities. The successful resolution of previous abort situation through procedural adjustments and operational execution demonstrates the resilience and adaptability that characterizes successful space programs throughout their history. The psychological experience following successful docking combines professional satisfaction with recognition of challenges overcome. The previous abort, initially disappointing operational setback, now transforms in perspective to become valuable learning opportunity that enabled ultimate success. This mental reframing represents essential characteristic of effective space operations. Setbacks become developmental steps when properly analyzed and incorporated into improved procedures, rather than simply obstacles to progress. Your module, now physically integrated with International Space Station, begins systems integration procedures beyond mechanical connection. Power interfaces establish shared electrical distribution, allowing optimization across combined resources. Data systems connect through multiple pathways, enabling coordinated operation and monitoring. Environmental systems harmonize control parameters to maintain consistent conditions across connected volumes. These integrations transform separate vehicles into functional components of unified system. The sensory environment continues evolving throughout post-docking activities. The air circulation patterns establish new equilibrium across connected modules. Temperature gradients stabilize between previously separate environments. Background sounds develop consistent patterns as systems operate in coordinated fashion. These ongoing adjustments happen largely below conscious awareness, yet contribute significantly to habitability of the integrated spacecraft complex. The culmination of successful docking extends far beyond technical achievement. The operation represents human ingenuity overcoming extraordinary challenges through combined application of engineering precision, operational discipline, and adaptive problem solving. The ability to join separate spacecraft traveling at orbital velocity stands among humanity's most impressive technical accomplishments, transforming theoretical possibility into operational reality through dedicated effort across decades of development. The experience leaves indelible impression regardless of how many previous dockings you might have participated in. Each successful connection between spacecraft represents triumph of human capability over environmental extremes and physical challenges that would have seemed insurmountable to previous generations. The progression from emergency abort through analysis, adjustment, and ultimately successful execution exemplifies the fundamental process that has enabled all human advancement in space exploration, learning from difficulty to build improved capability. As integration activities proceed following successful docking, the immediate operational intensity gradually transitions towards sustained routine. The environmental systems that maintained separate habitable volumes now function as integrated network. The structural connection that joined independent vehicles now provides platform for combined operations. The crew that coordinated across radio communications now interacts directly within shared environment. These transitions represent the ultimate purpose behind all docking challenges, creating unified operational capability greater than separate components could achieve independently. The sensory experience settles into new normality as hours pass following successful connection. The initial novelty of expanded environment gives way to functional familiarity. The background operations of environmental systems fade from conscious awareness into expected conditions. The structural connection between previously separate spacecraft becomes taken for granted rather than operational achievement. This progression from extraordinary accomplishment to operational routine represents the essential pattern of human adaptation that has characterized space exploration since its inception. This successful docking, with its preceding challenges and ultimate resolution, contains fundamental lessons applicable beyond spaceflight operations. The technical precision requirements demonstrate value of meticulous preparation and attention to detail. The emergency abort response shows importance of building resilient systems with appropriate safety margins. The recovery process exemplifies how setbacks become developmental opportunities when approached with analytical perspective rather than disappointment. The ultimate success illustrates how persistence guided by experience leads to achievement despite significant obstacles. The International Space Station continues its silent orbit against the backdrop of Earth and cosmos, now expanded by your successfully docked module. The combined structure traces its luminous path across the night side of the planet, visible to observers below as bright point moving with mathematical precision through star field. This visible manifestation of human engineering achievement continues its journey at 17,500 miles per hour, a technological triumph measured not just in orbital parameters, but in the expanded human capability it represents.